Next we have to find the shear force and bending moment and draw the diagrams for a simply supported beam at the two ends carrying the UDL of constant intensity small w per unit length. The length of the beam is L. Now you know that the beam is having a load which is equivalent to the intensity of loading W per unit length multiplied by the length, and this load is acting at its center of the beam because the loading is symmetrical. And the reactions at the two ends you can find by using the principle of equilibrium, which we did in the previous case, and you will find that this load is divided at the two ends because it is acting at the center, which is equal to W by 2, small WL by 2 on each end. Now we have to draw the shear force diagram first. So taking a section at a distance x from this end here, the shear force at this section is this load is acting in upward direction and the load contained in this length x is acting in downward direction. So R1 minus W into x. This is small w. So R1 is WL by 2 minus W into x. This is a straight line. So at x equal to 0, which I have shown here, Fx is WL by 2 equal to the reaction here WL by 2. This is positive. And if you put x equal to L, you will get Fx is minus WL by 2 equal to opposite of this reaction here. So we have the shear force is WL by 2 with a negative sign. And shear force will be 0. Obviously you can see that x equal to L by 2, where the effective load is acting, this will be changing its sign. This is minus, this is plus. So there is a change in intensity from this point to this point. At this point there is a change in intensity, it becomes 0, and this is because of the load which is acting here in the downward direction. So the intensity change is from WL by 2 minus WL by 2, which is equal to W into L, which is equal to the total load acting at this point. Now we can draw the bending moment diagram for this. What is the bending moment diagram? Let us write the equation for the bending moment of the beam. Mx at a distance x from this end A. What is the bending moment? Moment due to R1, R1x minus moment due to this load. The load is acting at its center. What is the load contained? Small w into x multiplied by the distance of the load. Point of application is at the center. Center to this section. This is x by 2. R1 x minus w x square by 2. So R1 is WL by 2. So this is W by 2 Lx minus x square. Because moment of this load about this section will be negative and this one is having positive moment. So you can see that this is the equation of a parabola. The nature of this is x square equal to minus k into y. So you can find the values at x equal to 0. What is the bending moment? This is 0. So here the bending moment is 0. At x equal to L, mx is also 0, because here we have only this load and there is no other load. So at points where the beam is simply supported, you will always find that the bending moment is 0. And what is the maximum bending moment? For M maximum, dm by dx is equal to 0. In other words, as per our previous discussion, we know that F is equal to dm by dx. Shear force was equal to rate of changing of bending moment. So when F is 0, dm by dx is 0. So where is the bending moment 0? At the point this point, center. So x equal to L by 2, and if you differentiate this, you will also find that at x equal to L by 2, the bending moment is 0. So M maximum is W by 2 L square by 2 minus L square by 4. So W L square divided by 8. So the diagram is like this. W L square divided by 8 is the maximum bending moment. So this is how we can draw the shear force and the bending moment diagram for this beam having a uniformly distributed load over the span.